Okay, this shouldn't take too long. You should have about 20 minutes to work either on the lab from yesterday or the homework problem. I got another worksheet for you to do based on what we're going to do here. Well, basically, the thought process is we're going to add a little bit each day. So basically, we're doing the exact same thing. It all comes down to how can we work with Newton's laws. And we've been working mostly with Newton's laws vertically, right? We talked about weight to begin with. Then we did drag force on objects acting vertically. Then we did the Atwood machine. And then yesterday, we kind of like tweaked that a little bit and took our wiffle ball and said, okay, we got some vertical stuff, but we also got some stuff acting at angles. And today, we're going to do something very similar. We're going to talk about the situation that makes this cart that makes this cart accelerate across the table. All right, so if I take this thing and I drop that down, this cart accelerates across the table. And we have a mixture of the cart moving horizontally and the hook moving vertically. So now, again, we are combining stuff that happens horizontally with stuff that happens vertically. Now, to start off, we would have talked about, hey, what happens when I take this thing and I drop it? That's vertical. We combine that by that vertical motion essentially, causing the horizontal motion of the cart. And we can just piece together those things by doing the exact same stuff that we've been doing. All right. Now, we use the cart because the cart essentially simulates a frictionless system. If the cart can simulate a frictionless system, we can work with horizontal-vertical combination without mentioning the idea of friction. So look, what do we have here? All right. I've got a system, just like we had a system back there when we worked on the Atwood machine stuff back there. I've got this system, and the system contains this cart, and the cart is attached to a weight or mass that's hanging over the end. Now we've got two things in the system, which means when I go to diagram this setup out, how many pictures do I need? I need 3 pictures. I need a picture for the cart, I need a picture for the hanging weight, and then I need a picture for the system. And so as this cart is being pulled across the table, give me a force that's acting on that cart, ladies. The tension is pulling this thing to the right. So I've got a tension force pulling it to the right. Now let me see what else I got on the cart. Yeah, we'll put the cart to make it frictionless. Next step will probably be do some stuff with friction. Yeah, its weight is going in the downward direction. Any other forces, Roy, acting on the cart? Yeah, the normal force is going upwards, right? Now, I don't know that we've utilized that. We might have when we talked about the elevator doing vertical stuff, right? We did actually. We did the skyscraper in the elevator. And there's a good depiction of what's happening with the cart. Callie, what about this hanging weight here? What do we got acting on that hanging weight? Yeah, its weight pulls down. So let's call this W sub C, and let's call this weight of, let's say, let's call it hook. Right? Weight of the hook. And then what's pulling the hook upwards? The tension is pulling the hook upwards. Now the system part of this is really where we have the intricacies. That makes it just a little bit tricky. Because, generally speaking, right, we saw that with the Atwood stuff back there. This is really what's happening. This is just kind of a rig version of what's happening so that we can, kind of use this to help us figure out what's going on. All right? Now, the difficult part here is that the system is working with some horizontal and some vertical. So the plane of motion for the system is a combination. The plane of motion for the system is horizontal up here and vertical for that object. In other words, when the hook falls down, it makes the cart go to the right on this picture. If I pull the cart to the left, then the hook would go up. So right for the cart is synonymous with down for the hook. Left for the cart is synonymous with up for the hook. And you can't get away with anything different. Now when we go to draw the system, right, that would mean then that only horizontal forces in the cart matter in the system. And only vertical forces with the hook matter in our system. Well, if I only have tension, tension, and weight, the two tensions do what for each other? They cancel each other out. So in reality here, the only force I've got acting is the weight of the hook on that system. Now again, probably tomorrow, we'll throw some friction there, and what happens? The friction will pull this system backwards because it's also in the horizontal. All right? All right. So now, let me ask you a couple questions. I've got this, oh, damn. All right. I got this cart right here. I got two separate questions for you. Okay? What happens to this scenario if I load a super lot of weight on that end and don't touch the cart? That's question number one. Question number two, what happens if I load a super lot of weight on the cart and leave the hook just like it is? So while I put this thing back up, I want you to answer those two questions, right? So what happens if, number one, all right, the hook is way heavier than the car? Number two, what happens if the car is way heavier than the hook? All right, so turn to some people around you. But while I'm doing this, talk about that setup with the people around. Go ahead.
We're on the car. In theory, should be right. But my brain wants to get it off. I mean,
because it's mass of the system. So there's the MA part.
my brain also.
And if that mass of the system is
All right, Olivia, what'd you come up with? What'd you come up with there?
So we said when the hook is way heavier than the car, it should accelerate faster than if there's no. The system should accelerate faster.
So when the hook is way heavier than the car, the acceleration is high.
Yeah.
That was your group set?
Yeah.
Okay.
We were debating the second one.
The car is way heavier than the hook. Now, what's your group set?
the car's still gonna move, but it's not gonna be as fast. Like the acceleration is lower.
So the acceleration is low. Anybody disagree with that? Jane,
Since the system's frictionless,
nice and loud.
shouldn't it be the same as if the car didn't have any added limits?
Yeah, that's often like a thought process, right? Like this is frictionless, so should it really have that effect? Because the weight is in this vertical point. Daniel, what do you have to say about that? That's an interesting debate.
the car's mass is included in the mass of the system. So when you do a net force equals ma, that part of that ma is the mass of the system, and the car's a part of that system. So when you increase the mass of the cart, you increase the mass of the system, which you would then have to divide over to the other side. And then if you divide by a big number, then the acceleration is going to be small.
Yes. Now, we're going to get back to that. What I want to go back to is, has anybody got anything more than this? Sleeves.
When you add mass, the falling weight, the acceleration would go up, but it would like approach 9.8, right? And when you add it to the car, it would approach 0.
So it's important as we start the end of your senior year, basically, this is kind of like, there's kind of two ends to this, in my experience. Starting back up in January can be tough. Starting back up in April is even harder. All right? Don't get lackadaisical and think we know everything and we don't want to go that extra mile. The extra mile is what Sleeves said, right? The math to this is what Tyler said. This I would expect you to be able to do in 15 seconds. All right? Now, having this in your mind. Now, how do we determine whether this is right or, Shannon was saying, she's like, oh, I don't know if that's right, or my AP brain, like, usually what I think is right is not right. Well, usually what we have to simply do is use math to illustrate that. All right? Now, is the system accelerating? 100%. So then, what do you know about the sum of the forces acting on the cart? The sum of the forces must be Ma. And what do we know about the sum of the forces on the hook? Must be Ma. And what do we know about the sum of the forces on the system? Must be Ma. Cart, system, hook. Now, what's the sum of the forces here? T is the value of the sum of our forces. It's the only horizontal force. And the cart is accelerating in the horizontal plane. What's the sum of our forces over here? Tyler out. What's the expression for the sum of the forces acting on the hook?
It would be the wouldn't it just be the tension minus the weight?
The fact that they're in opposite directions and we have a negative sign in there is good, but what direction do we always want to put positive? The direction of the acceleration. In what direction is the hook accelerating? Yeah, so we want to swap those. Here I got WH minus T as the sum of my forces. What's the sum of the forces over here, Yair?
The weight of the hook equals the mass of the system times
the weight of the hook equals the mass of the system times X. Well, how do we calculate the weight of the hook? Mass of the hook times G equals mass of the system. Now, what's the mass of the system? It's the mass of the hook plus the mass of the cart. Mass of the hook plus the mass of the cart times A. Now, I'm going to write it nice and big down here. A is equal to MH times G divided by MH plus MC. So let's go from just the 30-second version here to a little bit more in-depth version that Sleeves gave us. First off, if this hook, we're not hooked to anything, and I dropped it, what would it accelerate at? 9.8 meters per second every single second. Why? Because what would the force diagram look like? The force diagram would just look like that. This causes an acceleration of 9.8. If I add the tension pulling it up, no matter how little the tension is pulling it up, doesn't that tension pulling it up have to lower the net force and therefore lower the acceleration? 100%. So therefore, this acceleration can never exceed 9.8. Next thing, to address Anna's setup, as the cart gets bigger and 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 bigger, and the mass gets bigger and bigger and bigger, that's only affecting the vertical. Is that a part of this system? It is not a part of the system. The system, well, let me rephrase that. It's not a part of the force diagram with respect to the system, because the system's acceleration is horizontal for the cart and vertical for the weight. Now look at it. Tomorrow, what would that thing do? If I add mass and mass and mass and mass and mass and mass and mass to this, what's that do? If we have friction, it increases the friction. And friction is a force that acts in the horizontal plane. But if we're talking about a quote-unquote frictionless system, changing this doesn't have anything to do with our setup. All right? Now, as we add, wait, what if I took Rocco and sat him on the cart? Could that ever result, in our particular situation, in an acceleration of 0? No, because increasing this number never changes anything in the horizontal. Right? Now look at math. Why do we have this thing approaching 9.8? Well, look at it. If the mass of the hook is 1,000, and the mass of the cart is 1, basically all I have here is A equals a multiplying factor times G. What if the mass of the hook is 1,000 and the mass of the cart is 1,000, or is 1 rather? Then what's my fraction? 1,000 over what? 1,001. What's that approaching? The fraction is approaching 1, which means my acceleration is approaching 9.8. Will it ever get to 9.8? Mathematically, it can't. What if I do the opposite? What if the cart has a mass of 1,000 and the hook has a mass of 1? What's my multiplying factor then? 1 over 1,001 times G. What's that approaching? 0. Will it ever get to 0? No. So this is the short version. Use math to get the longer, more in-depth version and have a higher level of understanding of what's going on. Ultimately, we still need our diagrams and our sum of the forces. All right? Now I've got a worksheet for you with 2 of these questions on them. All right? We're going to add that to what you already have assigned. We'll make